Have you ever stopped to think about the best pieces of technology in your life? They kind of just work. They feel invisible, almost like magic. Well, today we're going to pull back that curtain and really look at the core engineering principles that make that so-called magic happen. And, this quote from the legendary Alan Kay just hits the nail on the head. The ultimate goal of great system design is to create something so dependable, so rock solid, that it just fades into the background of our lives. But as you can imagine, getting to that point is a monumental challenge. So, what's the single biggest hurdle we face when building apps today? Well, for most systems, it's actually not about raw processing power anymore. It's not about the CPU. The real bottleneck is the data itself. We're talking about managing a massive volume of it, handling its incredible complexity, and keeping up with the dizzying speed at which it all changes. The name of the game is data. The good news is, we're not starting from square one every time. We build modern applications by combining these standard, battle-tested components, things like databases to store information, caches to make reading it faster, search indexes to help us find it, and when you start stitching these pieces together, you're not just building an app, you're actually designing a brand new, special-purpose data system. To do this well, we need a mental model, a framework to guide our decisions. And it turns out we can boil down most of our big concerns into three fundamental pillars: reliability, scalability, and maintainability. Get these three right, and you're well on your way to building something that can truly stand the test of time. So here's our game plan for this explainer. We're going to tackle each of these pillars one by one. First, how to deal with things when they break. Second, how to handle success and growth. And third, how to manage the only real constant, which is change. All right, let's dive right into our first and arguably most important pillar: reliability. At its core, this is all about a very simple promise: making sure your system keeps doing what it's supposed to do, even when things inevitably, and I mean inevitably, go wrong. So what does working correctly actually mean? Well, it means the system does what the user expects, and it does it with a reasonable level of performance. We also call this being fault-tolerant or resilient. The idea is to anticipate problems before they happen and design the system to handle them gracefully. Now, this slide highlights a really critical distinction. A fault is when one little piece of the system messes up. Maybe a single server's hard drive crashes. A failure, on the other hand, is when the whole system goes down and the user can't get their job done. Our goal as engineers isn't to prevent every single fault. That's literally impossible. Our job is to build systems that can withstand faults without causing a total failure. So, where do these faults come from? Well, you can pretty much lump them into three big categories. Hardware can and will fail. Software will always have bugs. And then there's us, humans. We make mistakes. In fact, a study of large internet services found that plain old configuration errors by operators were the #1 cause of outages. So you have to design for all three. Okay, let's shift gears to our second pillar: scalability. You see, a system that works perfectly fine for 1,000 users might completely fall apart when 1,000,000 show up. Scalability is all about our strategy for handling that kind of growth. So when we talk about scalability, we're really asking two main questions. One, if our load, say the number of users, doubles or triples, what are our options for handling it? And two, how can we add more resources, more computing power, to cope with that increase without breaking the bank or redesigning the whole thing? Twitter is just a fantastic case study here. You'd think their biggest problem would be just handling the sheer number of tweets being posted every second. But the real monster they have to deal with is something called fan-out. That's the challenge of taking one person's tweet and delivering it to the home timelines of their potentially millions of followers. The number of timeline reads is just orders of magnitude higher than the number of tweets being written. So, in the early days, Twitter used what we'd call a pull approach. When you wanted to see your timeline, their servers would go and find all the tweets from people you follow and stitch them together right then and there. But as you can guess, that got incredibly slow. So they flipped it to a push model. Now, when a popular user tweets, Twitter does all the heavy lifting up front, pushing that tweet into a ready-made timeline for every single follower. That's why loading your timeline feels so fast. Now, when we talk about performance, we have to be precise with our language. Latency is just the time a request is sitting there, idle, waiting for its turn to be handled. Response time, on the other hand, is the whole shebang. It's the total time the user experiences from the moment they click to the moment they get a result. It includes network lag, time spent in queues, everything. And response time is what really matters, because that's what the user feels. This is why looking at the average response time is a classic rookie mistake. The average can easily hide some really terrible performance for a subset of your users. Instead, we have to look at percentiles. The median, or P50, tells you what a typical user experience is. But the high percentiles, like the 95th or 99th, tell you what your unluckiest users are experiencing. And get this, Amazon found that the customers with the slowest request times were often their best customers, the ones with huge shopping carts and long order histories. Now, here's a concept that's absolutely crucial for senior engineers to understand. Most of the time, to load a single web page, your system has to make calls to several different backend services, and the user has to wait for the slowest one of those calls to finish. This means that even a small percentage of slow backend calls can snowball, causing a large percentage of user-facing requests to be slow. We call this tail latency amplification, and it's exactly why we obsessed over those high percentiles. And that brings us to our third and final pillar, maintainability. You could say that reliability is about the present, and scalability is about the future, but maintainability, that's all about the people. It's the human side of engineering, and it's a constant battle against growing complexity. This is just one of the hard truths of our industry. The real cost of a piece of software isn't building it the first time around. Nope. It's the years or even decades spent fixing bugs, adapting it to new business needs, and just generally keeping the lights on. Good software design is really about making life easier for the next engineer who has to work on your code. So how do we achieve that? Well, we can break it down into three main principles. First, operability. Make it easy for the operations team to keep the system healthy. Second, simplicity. Fight like crazy to remove unnecessary complexity so people can actually understand the system. And third, evolvability. Make it easy and safe for other engineers to make changes down the road. When we talk about simplicity, what we're really fighting is something called accidental complexity. This isn't the natural, inherent complexity of the business problem we're trying to solve. This is the extra mess that we introduce through our implementation choices. And our single best weapon in this fight is abstraction. Think about SQL. It is a perfect example of a brilliant abstraction. When you write a simple select query, you have no idea about the mind-bogglingly complex machinery working under the hood, managing how data is laid out on disk, handling multiple people trying to access it at once, recovering from crashes. A great abstraction hides all of that implementation mess behind a clean, simple interface. That's what makes a system maintainable. All right, let's bring it all home. These three pillars, reliability, scalability, and maintainability, they aren't just a simple checklist. They really form a unified philosophy for how to think about building systems that are designed to last. So, let's just quickly recap the big ideas. Reliability is our foundation. We build systems that can tolerate faults so they don't fail our users. On top of that, we engineer for scalability, using percentiles, not averages, to measure the real user experience as we grow. And weaving through all of it is maintainability, where we use powerful abstractions to wrestle complexity to the ground, ensuring our system can adapt and evolve for years to come. So, the next time you open an app on your phone and it just works flawlessly, take a second and think about it. What invisible engineering, what delicate balance of reliability, scalability, and maintainability had to come together perfectly right behind the scenes to create that seamless, almost magical experience for you?